Welcome to this video on Ampere's Circuital law for CBSE and NIOS Class 12 students. This is an important concept in electromagnetism that helps us understand how electric currents generate magnetic fields. Let's begin with the statement of Ampere's Circuital law. The closed line integral of the magnetic field intensity B around any closed path is equal to mu naught times the net electric current I enclosed piercing the surface bounded by that path. Mathematically, this is expressed as the integral of B dot dl around a closed loop C equals mu naught times I enclosed. Here, mu naught is the permeability of free space, which equals 4 pi times 10 to the minus 7 henries per meter. Let's understand what these symbols mean. C represents a closed curve, which we call an Amperian loop. dl is an infinitesimal element of length along this curve C, taken in the chosen direction of integration. I enclosed is the algebraic sum of all currents passing through any surface that spans the closed curve C. An important aspect of Ampere's law is the right-hand rule. To determine the relationship between the direction of integration and the direction of current, we use the right-hand rule. If you curl the fingers of your right hand along the direction of integration dl, your thumb points in the direction of the net current I enclosed. So if we integrate counterclockwise around our loop, the current is considered positive when it points out of the plane. Now, let's apply Ampere's law to find the magnetic field of a long straight conductor. Consider a long straight wire carrying a current I. We choose a circular Amperian loop of radius are centered on the wire. By symmetry, the magnitude of the magnetic field, B, is constant everywhere on this loop and is tangent to it. This means our line integral simplifies to B times the circumference of the circle. So the integral of B dot dl equals B times 2 pi r. Now the enclosed current, I enclosed, is simply I, the current flowing through the wire. Using Ampere's law, we can write B times 2 pi r equals mu naught times I. Solving for B, we get B equals mu naught times I divided by 2 pi r. This is the well-known formula for the magnetic field, due to a long straight current-carrying conductor at a distance are from its axis. Before we tackle a numerical problem, let's note some important points about Ampere's law. First, only currents piercing the chosen surface count. Currents that pass outside the Amperian loop have no effect. Second, if multiple currents pass through the surface, we take their algebraic sum. Currents directed outward are considered positive, while those directed inward are negative. Third, for time-varying fields, Maxwell's displacement current term must be added, but this is beyond the scope of grade 12. Let's solve a sample problem. A long straight wire carries a steady current of 5.0 amperes. Find the magnetic field at a distance of 4.0 centimeters from its axis. We'll use the formula we derived, B equals mu naught times I divided by 2 pi r. Substituting the values, mu naught equals 4 pi times 10 to the minus 7 henries per meter, I equals 5.0 amperes, and R equals 4.0 centimeters, which is 0.04 meters. Calculating, B equals 4 pi times 10 to the minus 7 times 5.0 divided by 2 pi times 0.04. This gives us B equals 2.5 times 10 to the minus 5 Tesla. Let's visualize this magnetic field. According to the right-hand rule, if we point our right thumb in the direction of the current, our fingers curl in the direction of the magnetic field. The strength of the magnetic field decreases with distance from the wire. As we've seen in our formula, B equals mu naught I divided by 2 pi r. This means the field is inversely proportional to the distance from the wire. If we double the distance, the field strength becomes half. To summarize what we've learned about Ampere's Circuital law, it states that the closed line integral of the magnetic field around any closed path equals mu naught times the enclosed current. We use the right-hand rule to determine the relationship between the direction of integration and the current direction. For a long straight wire, the magnetic field at a distance R is given by B equals mu naught I divided by 2 pi r. Remember, Ampere's law is one of Maxwell's equations and is fundamental to understanding electromagnetism. Thank you for watching. I hope this helps with your CBSE or NIOS Class 12 physics preparation.